really excited to be here. I think it was almost 4 years ago to the day that we were about 20 people sitting in a small conference room in one of the Google buildings. We've woken up early because we wanted to kind of time this for an early East Coast launch where we were turning on the TensorFlow.org website and releasing the first version of TensorFlow as an open source project. And I'm really, really excited to see what it's become. It's just remarkable to see the growth and all the different kinds of ways in which people have used this system for all kinds of interesting things around the world. So one thing that's interesting is the growth in the use of TensorFlow also kind of mirrors the growth in interest in machine learning and machine learning research generally around the world. So this is a graph showing the number of machine learning archive papers that have been posted over the last sort of 10 years or so. And you can see it's growing quite rapidly, much more quickly than you might expect. And that lower red line is kind of the nice doubling every couple of years growth rate, exponential growth rate we got used to in computing power due to Moore's law for so many years. That's now kind of slowed down. But you can see that the machine learning research community is generating research ideas at faster than that rate, which is pretty remarkable. We've replaced computational growth with growth of ideas, and we'll see those both together will be important. And really, the excitement about machine learning is because we can now do things we couldn't do before, right? As little as 5 or 6 years ago, computers really couldn't see that well. And starting in about 2012, 2013, we started to have people use deep neural networks to try to tackle computer vision problems, image classification, object detection, things like that. And so now, using deep learning and deep neural networks, you can feed in the raw pixels of an image and fairly reliably get a prediction of what kind of object is in that image. Feed in the pixels there, red, green, and blue values in a bunch of different coordinates, and you get out the prediction leopard. This works for speech as well. You can feed in audio waveforms, and by training on lots of audio waveforms and transcripts of what's being said in those waveforms, we can actually take a completely new recording and tell you what is being said, emit a transcript. Bonjour, comment allez-vous? You can even combine these ideas and have models that take in pixels, and instead of just predicting classifications of what is in the object, can actually write a short sentence, a short caption that a human might write about the image. A cheetah lying on top of a car. That's one of my vacation photos, which was kind of cool. And so just to show the progress in computer vision, in 2011, Stanford hosts an ImageNet contest every year to see how well computer vision systems can predict one of 1,000 categories in a full-color image. And you get about 1 million images to train on, and then you get a bunch of test images your model has never seen before, and you need to make a prediction. In 2011, the winning entrant got 26% error, right? So you can kind of make out what that is, but it's pretty hard to tell. We know from a human experiment that the human error of a well-trained human, someone who's practiced at this particular task and really understands the 1,000 categories, gets about 5% error. So it's not a trivial task. And in 2016, the winning entrant got 3% error. So just look at that tremendous progress in the ability of computers to resolve and understand computer imagery and have computer vision that actually works. This is remarkably important in the world because now we have systems that can perceive the world around us, and we can do all kinds of really interesting things with that. We've seen similar progress in speech recognition and language translation, things like that. So for the rest of the talk, I'd like to kind of structure it around this nice list of 14 challenges that the US National Academy of Engineering put out and felt like these were important things for the science and engineering communities to work on for the next 100 years. They put this out in 2008 and came up with this list of 14 things after some deliberation. And I think you'll agree that these are sort of pretty good, large, challenging problems that if we actually make progress on them, that we'll actually have a lot of progress in the world. We'll be healthier, we'll be able to learn things better, we'll be able to develop better medicines, we'll have all kinds of interesting energy solutions. So I'm going to talk about a few of these. And the first one I'll talk about is restoring and improving urban infrastructure. So we're on the cusp of the sort of widespread commercialization of a really interesting new technology that's going to really change how we think about transportation, and that is autonomous vehicles. And this is a problem that has been worked on for quite a while, but it's now starting to look like it's actually completely possible and commercially viable to produce these things. And a lot of the reason is that we now have computer vision and machine learning techniques that can take in sort of raw forms of data that the sensors on these cars collect. So they have like the spinning LiDARs on the top that give them 3D point cloud data. They have cameras in lots of different directions. They have radar in the front bumper and the rear bumper. And they can really take all this raw information in and with a deep neural network, fuse it all together to build a high-level understanding of what is going on around the car. Or is it like another car to my side? There's a pedestrian up here to the left. There's a light post over there. I don't really need to worry about that moving. And really help to understand the environment in which they're operating, and then what actions can they take in the world that are both legal, safe, obey all the traffic laws, and get them from A to B. And this is not some distant, far-off dream. Alphabet's Waymo subsidiary has actually been running tests in Phoenix, Arizona. Normally, when they run tests, they have a safety driver in the front seat ready to take over if the car does something kind of unexpected. But for the last year or so, they've been running tests in Phoenix with real passengers in the back seat and no safety drivers in the front seat, running around suburban Phoenix. So suburban Phoenix is a slightly easier training ground than, say, downtown Manhattan or San Francisco, but it's still something that is like not really far off. It's something that's actually happening. And this is really possible because of things like machine learning and the use of TensorFlow in these systems. Another one that I'm really, really excited about is advanced health informatics. This is a really broad area, and I think there's lots and lots of ways that machine learning and the use of healthcare data can be used to make better healthcare decisions for people. So I'll talk about one of them. And really, I think the potential here is that we can use machine learning to bring the wisdom of experts through a machine learning model anywhere in the world. And that's really a huge, huge opportunity. So let's look at this through one problem we've been working on for a while, which is diabetic retinopathy. So diabetic retinopathy is the fastest growing cause of preventable blindness in the world. And screening every year, if you're at risk for this, and if you have diabetes or early sort of symptoms that make it likely you might develop diabetes, you should really get screened every year. So there's 400 million people around the world that should be screened every year. But the screening is really specialized. Doctors can't do it. You really need an ophthalmologist level of training in order to do this effectively. And the impact of this shortage is significant. So in India, for example, there's a shortage of 127,000 eye doctors to do this sort of screening. And as a result, 45% of patients who are diagnosed with this disease actually have suffered either full or partial vision loss before they're actually diagnosed and then treated. And this is completely tragic because this disease, if you catch it in time, is completely treatable. There's a very simple 99% effective treatment that we just need to make sure that the right people get treated at the right time. So what can you do? So it turns out diabetic retinopathy screening is also a computer vision problem. And the progress we've made on general computer vision problems, where you want to take a picture and tell if that's a leopard or an aircraft carrier or a car, actually also works for diabetic retinopathy. So you can take a retinal image, which is what the screening camera, sort of the raw data that comes off the screening camera, and try to feed that into a model that predicts 1, 2, 3, 4, or 5. That's how these things are graded. 1 being no diabetic retinopathy, 5 being proliferative, and the other numbers being in between. So it turns out you can get a collection of data of retinal images and have ophthalmologists label them. Turns out if you ask 2 ophthalmologists to label the same image, they agree with each other 60% of the time on the number 1, 2, 3, 4, or 5. But perhaps slightly scarier, if you ask the same ophthalmologist to grade the same image a few hours apart, they agree with themselves 65% of the time. But you can fix this by actually getting each image labeled by a lot of ophthalmologists. So you get it labeled by 7 ophthalmologists. If 5 of them say it's a 2 and 2 of them say it's a 3, it's probably more like a 2 than a 3. Eventually, you have a nice high-quality data set you can train on. Like many machine learning problems, high-quality data is the right raw ingredient. But then you can apply basically an off-the-shelf computer vision model trained on this data set. And now you can get a model that is on par or perhaps slightly better than the average board-certified ophthalmologist in the US, which is pretty amazing. It turns out you can actually do better than that. And if you get the data labeled by retinal specialists, people who have more training in retinal disease and change the protocol by which you label things, you get 3 retinal specialists to look at an image, discuss it amongst themselves, and come up with what's called a sort of coordinated assessment and one number, then you can train a model and now be on par with retinal specialists, which is kind of the gold standard of care in this area. And that's something you can now take and distribute widely around the world. So one issue particularly with healthcare kinds of problems is you want explainable models. You want to be able to explain to a clinician, why is this person, why do we think this person has moderate diabetic retinopathy? And so you can take a retinal image like this, and one of the things that really helps is if you can show in the model's assessment why this is a 2 and not a 3. And by highlighting parts of the input data, you can actually make this more understandable for clinicians and enable them to really get behind the assessment that the model is making. And we've seen this in other areas as well. There's been a lot of work on explainability, so I think the notion that deep neural networks are sort of complete black boxes is a bit overdone. There's actually a bunch of good techniques that are being developed and more all the time that will improve this. So a bunch of advances depend on being able to understand text. And we've had a lot of really good improvements in the last few years on language understanding. So this is a bit of a story of research and how research builds on other research. So in 2017, a collection of Google researchers and interns came up with a new kind of model for text called the transformer model. So unlike recurrent models where you have kind of a sequential process where you absorb one word or one token at a time and update some internal state and then go on to the next token, the transformer model enables you to process a whole bunch of text all at once in parallel, making it much more computationally efficient, and then to use attention on previous text to really focus on, if I'm trying to predict what the next word is, what are other parts of the context to the left that are relevant to predicting that. So that paper was quite successful and showed really good results on language translation tasks with a lot less compute. So the blue score there in the first 2 columns for English to German and English to French, higher is better. And then the compute cost of these models shows that this is getting sort of state-of-the-art results at that time with 10 to 100x less compute than other approaches. Then in 2018, another team of Google researchers built on the idea of transformers. So everything you see there in a blue oval is a transformer module. And they came up with this approach called bidirectional encoding representations from transformers, or BERT. It's a little bit shorter and more catchy. So BERT has this really nice property that in addition to using context to the left, it uses context all around the language, the surrounding text, in order to make predictions about text. And the way it works is you start with a self-supervised objective. So the one really nice thing about this is there's lots and lots of text in the world. So if you can figure out a way to use that text to train a model to be able to understand text better, that would be great. So we're going to take this text, and in the BERT training objective, to make it self-supervised, we're going to drop about 15% of the words. And this is actually pretty hard, but the model is then going to try to fill in the blanks, essentially. Try to predict what are the missing words that were dropped. And because we actually have the original words, we now know, if the model is correct in its guesses about what goes in the blanks. And by processing trillions of words of text like this, you actually get a very good understanding of contextual cues in language and how to actually fill in the blanks in a really intelligent way. And so that's essentially the training objective for BERT. You take text, you drop 15% of it, and then you try to predict those missing words. And one key thing that works really well is that's step 1. You can pre-train a model on lots and lots of text using this fill-in-the-blanks self-supervised objective function. And then step 2, you can then take a language task you really care about. Like maybe you want to predict, is this a 5-star review or a 1-star review for some hotel? But you don't have very much labeled text for that actual task. You might have 10,000 reviews and know the star count of each review. But you can then fine-tune the model, starting with the model trained in step 1 on trillions of words of text, and now use your paltry 10,000 examples for the text task you really care about. And that works extremely well. So in particular, BERT gave state-of-the-art results across a broad range of different text understanding benchmarks in this GLUE benchmark suite, which was pretty cool. And people have been using BERT now in this way to improve all kinds of different things all across the language understanding and NLP space. So one of the grand challenges was engineer the tools of scientific discovery. And I think it's pretty clear machine learning is actually going to be an important component of making advances in a lot of these other grand challenge areas, things like autonomous vehicles or other kinds of things. And it's been really satisfying to see what we'd hoped would happen when we released TensorFlow as an open source project has actually kind of come to pass as we were hoping, in that lots of people would sort of pick up TensorFlow, use it for all kinds of things. People would improve the core system. They would use it for tasks we would never imagine. And that's been quite satisfying. So people have done all kinds of things. Some of these are uses inside of Google. Some are outside in academic institutions. Some are scientists working on conserving whales or understanding like ancient scripts. Many kinds of things, which is pretty neat. The breadth of uses is really amazing. These are the 20 winners of the Google.org AI Impact Challenge, where people could submit proposals for how they might use machine learning and AI to really tackle a local challenge they saw in their communities. And they have all kinds of things, ranging from like trying to predict better ambulance dispatching to identifying illegal logging using speech recognition or audio processing. Pretty neat. And many of them are using TensorFlow. So one of the things we're pretty excited about is AutoML, which is this idea of automating some of the process by which machine learning experts sit down and sort of make decisions to solve machine learning problems. So currently, you have a machine learning expert sit down, they take data, they have computation, they run a bunch of experiments, they kind of stir it all together, and eventually you get a solution to a problem you actually care about. One of the things we'd like to be able to do, though, is see if we could eliminate a lot of the need for the human machine learning expert to run these experiments and instead automate the experimental process by which a machine learning expert comes by a high-quality solution for a problem you care about. So one of the lots and lots of organizations around the world have machine learning problems, but many of them don't even realize they have a machine learning problem, let alone have people in their organization that can tackle the problem. So one of the earliest pieces of work our researchers did in this space was something called neural architecture search. So when you sit down and design a neural network to tackle a particular task, you make a lot of decisions about shapes of this or that, and like should it be used 3x3 filters at layer 17 or 5x5, all kinds of things like this. It turns out you can automate this process by having a model generating model and train the model generating model based on feedback about how well the models that it generates work on the problem you care about. So the way this will work, we're going to generate a bunch of models. Those are just descriptions of different neural network architectures. We're going to train each of those for a few hours, and then we're going to see how well they work, and then use the accuracy of those models as a reinforcement learning signal for the model generating model to steer it away from models that didn't work very well and towards models that worked better. And we're going to repeat many times. And over time, we're going to get better and better by steering the search to the parts of the space of models that worked well. And so it comes up with models that look a little strange, admittedly. A human probably would not sit down and wire up a sort of machine learning computer vision model exactly that way, but they're pretty effective. So if you look at this graph, this shows kind of the best human machine learning experts, computer vision experts, machine learning researchers in the world producing a whole bunch of different kinds of models in the last 4 or 5 years, things like ResNet 50, DenseNet 201, Inception ResNet, all kinds of things. That black dotted line is kind of the frontier of human machine learning expert model quality on the y-axis and computational cost on the x-axis. So what you see is as you go out the x-axis, you tend to get more accuracy because you're applying more computational cost. But what you see is the blue dotted line is AutoML-based solutions, systems where we've done this automated experimentation instead of pre-designing any particular architecture. And you see that it's better both at the high end, where you care about the most accurate model you can get, regardless of computational cost, but it's also accurate at the low end, where you care about a really lightweight model that might run on a phone or something like that. And in 2019, we've actually been able to improve that significantly. This is a set of models called EfficientNet and has a very sort of a slider about you can trade off computational cost and accuracy. But they're all way better than human sort of guided experimentation on the black dotted line there. And this is true for image recognition, for classification. It's true for object detection. So the red line there is AutoML. The other things are not. It's true for language translation. So the black line there is various kinds of transformers. The red line is we gave the basic components of transformers to an AutoML system and allowed it to fiddle with it and come up with something better. It's true for computer vision models used in autonomous vehicles. So this is a collaboration between Waymo and Google Research. We were able to come up with models that are, significantly lower latency for the same quality, or they could trade it off and get significantly lower error rate at the same latency. It actually works for tabular data. So if you have lots of customer records and you want to predict which customers are going to be spending $1,000 with your business next month, you can use AutoML to come up with a high quality model for that kind of problem. Okay, so what do we want? I think we want the following properties in a computer in a machine learning model. So one is we tend to train separate models for each different problem we care about. I think this is a bit misguided. Really, we want one model that does a lot of things so that it can build on the knowledge in how it does thousands or millions of different things, so that when the million and first thing comes along, it can actually use its expertise from all the other things it knows how to do to know how to get into a good state for the new problem with relatively little data and relatively little computational cost. So these are some nice properties. I have kind of a cartoon diagram of something I think might make sense. So imagine we have a model like this, where it's very sparsely activated. So different pieces of the model, have different kinds of expertise, and they're called upon when it makes sense, but they're mostly idle. So it's relatively computationally and power efficient, but it can do many things. And now each component here is some piece of a machine learning model with different kinds of state, parameters in the model, and different operations. And a new task comes along. Now, you can imagine something like neural architecture search becoming squint at it just right and now turn it into neural pathway search. We're going to look for components that are really good for this new task we care about. And maybe we'll search and find that this path through the model actually gets us into a pretty good state for this new task, because maybe it goes through components that are trained on related tasks already. And now maybe we want that model to be more accurate for the purple task. So we can add a bit more computational capacity, add a new component, start to use that component for this new task, continue training it, and now that new component can also be used for solving other related tasks. And each component itself might be running some sort of interesting architectural search inside it. So I think something like that is the direction we should be exploring as a community. It's not what we're doing today, but I think it could be a pretty interesting direction. Okay. And finally, I'd like to touch on thoughtful use of AI in society. As we've seen more and more uses of machine learning in our products and around the world, it's really, really important to be thinking carefully about how we want to apply these technologies. They can, like any technology, these systems can be used for amazing things or things we might find a little sort of detrimental in various ways. And so we've come up with a set of principles by which we think about applying sort of machine learning and AI to our products. And we've made these public about 1.5 years ago as a way of sort of sharing our thought process with the rest of the world. And I particularly like these. I'll point out many of these are sort of areas of research that are not fully understood yet, but we aim to apply the best in the state-of-the-art methods for example, for reducing bias in machine learning models, but also continue to do research and advance the state-of-the-art in these areas. And so this is just kind of a taste of different kinds of work we're doing in this area. How do we do machine learning with more privacy using things like federated learning? How do we make models more interpretable so the clinician can understand the predictions it's making on diabetic retinopathy sort of examples? How do we make machine learning more fair? OK, and with that, I hope I've convinced you that deep neural nets and machine learning, you're already here, so maybe you're already convinced of this, but are helping make sort of significant advances in a lot of hard computer science problems. Computer vision, speech recognition, language understanding, general use of machine learning is going to push the world forward. So thank you very much, and I appreciate you all being here.